So this was a particular challenge, and I'm going to talk about what makes it so challenging in a moment. But first let me survey and see who has any answer. Give me a thumbs up if you have any answer at all. I got a couple people. 1, 2, 3, 4. Okay. John, we'll start with you, then we'll go to Alexandra, then Sharik, and then Ziomara.
Well, my ratio is variables, and for every circle, if you circumscribe, like this, square inside of it, the square.
Inside means inscribed, circumscribed means outside.
Well, it works the same way, because if you do it on the outside, then you draw a circle around the square, it'd be the same ratio as the smaller circle inside the square. And if you keep doing the same thing, the square, the circle will get bigger and bigger. But have the
That's true, it does, but I'm looking for specifically what ratio it would be. So you're on to something, but we need to get a little bit more formal. Go ahead, Alexandra, what'd you get?
1.05.
Okay, Sharik,
I got 1 to 2.
Ziomara, and you said 1.05 to 2.05, so that's pretty close to 1 to 2. And so yeah, it comes out to 1 to 2. And Alexandra, again, you did it correctly. Yours slight differentiation has to do with rounding. That's really it. So this challenge was particularly difficult because there are no numbers. So how do we go from no numbers to numbers? That's very difficult. And that's why we only had 1/4 approximately of the population of the class able to get anywhere. So part of this is a learning tool. This is a moment for you to now start going beyond what your experience has taught you, which is you need information to get information. You actually don't. You have to create some things from your mind. So let's start with the first bit. And most of you have diagrams you can fill in. Let's just start with the small circle. If we draw in that line right there, what is that line called? It has a name. David? It's a radius. What letter do we usually use for that, Dayanara? We usually use an R. So how about we just label it R? Now, I would like the area of the small circle. What's the area of the small circle? Nathaniel? Pi r squared. So the small circle's area is pi r squared. So we're asked to write a ratio of the smaller circle to the larger one, the areas. We already have the area of the small one. I know it's not a number, but we have the area. Now we need the area of the larger circle. So where's the radius of the larger circle? Could someone describe how I would have to do that? How would I draw the radius of the larger circle? Kamoy? To say that again. That's right. From the center of the circle to the vertex of the square is actually the radius of the larger circle. Here's the magic. Let me complete the picture for you. This is a magical triangle. Can someone fill in a detail about that triangle? Anything at all? Let me move this R a little bit so it's out of the way. So that's R. We already know that that's R. Fill in something else. Anything at all? Alexandra? Very good. This turns out to be R as well, because what type of triangle is this? Well, it is a right triangle, but what detail makes that R and that R? It's going to be a kick yourself moment. It's isosceles. That's what makes the legs equal to each other. And I love how you said the leg. Okay, you also revealed another detail that I was going to call on somebody else for, but this is now a right triangle, right? What else can we fill in, Kimoy? It's a 45, 45, 90 because this is also the diagonal of a square. And so that's cutting this into a 45-degree angle. So this is 45 degrees, and this is 45 degrees. Do that a little bit better. So we're trying to find the area of the big circle. We need that right there. The distance here. What is it? Eric?
It would be the radius times radical 2.
Exactly. Because how did you get that?
Because in a 45, 45, 90 triangle, the hypotenuse would be radical 2 times the length of the...
Exactly. So the hypotenuse of a 45, 45, 90 right triangle is going to be the leg times radical 2. So now we have everything we need. We've got the area of the small circle. The area of the large circle is going to be pi r squared, but now r is this. So pi r radical 2 squared. So Sharik, when we simplify r radical 2 squared, what does it actually turn into?
2r squared.
Comes out to 2r squared. So the large circle is actually 2 pi r squared. And we were asked for the ratio of the smaller circle to the larger one. Put them on top of each other. Pi r squared over 2 pi r squared. Pi cancels pi. R squared cancels r squared. You got 1 over 2. So this certainly was not easy. Not easy by any stretch of the imagination. But again, it was supposed to be an experience, one that challenged you to, maybe for the first time, I don't know if it's the first time, but maybe for the first time, introduce the idea that you can actually get something when there's nothing there by using your prior knowledge and your abilities and creativity. Does anyone have any questions about how we approached this? How we got to the result? Anything at all? Anything at all? Good. Those of you who persevered through it, who worked hard on creativity and just trying to figure it out, I applaud your efforts. You should be proud of yourself. So, today, of course, you titled your lesson 11.5. Today we're going to leap to three-dimensional objects, solids. We're going to start laying the foundation for working with solid figures. Some particular in particular. So, some of our goals today are to be able to classify some solids, and we're going to learn about cross sections and how we can use that to analyze three-dimensional figures. A lot of new terminology coming out today. Face, edge, prism, cylinder, pyramid, cross section. Some of these terms you may have heard before, but maybe not in this context. Any observations or questions so far? So I have another paper I'm going to give you to help us work through today because we got a lot of complex diagrams. So take one copy, team leaders, and pass the rest over, please. And I would not staple it right away because it's double-sided. You're going to need the pictures on the back. And we could staple it in at the end. Anyone not get one? I haven't labeled the pictures because you don't need me to. The picture will be up here. You look down there, find the one that applies. And the purpose of me doing this for you is so that you can mark up the picture. Use it to write things, mark things, indicate things, whatever you want. Okay? So, first of all, this is not for you to copy. This is for us to digest. You're going to be experiencing it so much that it's not something you need a reference to. First of all, another new term, polyhedron. A polyhedron is a three-dimensional figure, a three-dimensional shape, a solid that's made up of polygons. We're going to have solids that are not made up of polygons, but today we're going to explore almost exclusively polyhedron. And so each face, each side of the polyhedron is called a face. When the faces meet, they meet at an edge. When multiple faces meet at a corner, that's called a vertex. So you have everything illustrated here. This is a rectangular prism. Here's an example of a face. Here's an example of an edge, and here's an example of a vertex. One of the things we're going to be exploring today is how many faces, how many edges, and how many vertices. One last note. The plural of polyhedron is polyhedra. Any comments or questions so far? Going to be quite a bit of groundwork. So, types of solids. We have, just to make sure we're clear on polyhedron versus non-polyhedron. Polyhedron has faces. The ones that are not may have a face, but also has a curved part. Once you introduce a curve, it is no longer a polyhedron. To name a polyhedron, you can name it as a prism, a pyramid, and you use the shape of the base in addition to that. So, for example, this is not just a prism, but this would be called a rectangular prism. This is not just a pyramid, but this would be called a rectangular pyramid. Any questions about that? Any concerns? All right. So now, regular, convex, and concave. Regular has the same meaning that it always has had. It means all the distances are the same. In this case, all the faces are the same. They're all congruent. A polyhedron is convex if it's like this. It's concave if it's like this. This one is also regular because all of the faces are the same. This one is irregular or non-regular because all the faces are not the same. Convex, concave. I struggle, I get confused between the words. I personally focus on concave. For some reason, since I was a kid, I've understood concave meant that there was like a dip in it, something that's concave. So anytime there's a part of the solid that kind of goes in on itself, that's going to be concave. If it doesn't, then it's convex. Any questions about that? Good. So this is all foundation for what we're going to be doing. Lastly, this is for you to copy down. This is something you're going to have to refer back to. I have found already that I have trouble remembering which letter goes where, so you might need a reference. Euler's theorem. Euler states that there is a relationship between the number of faces, the number of vertices, and the number of edges for any polyhedron. The number of faces plus the number of vertices is always going to equal the number of edges plus 2. So I do not want you to draw these pictures or anything like that. These pictures are here for us to use. And they're also here to hammer home the idea of how to name a shape. I also have more down here. So, triangular prism. This is a prism. These are all prisms. This is a triangular prism because the base is a triangle. This base is a rectangle. This base is a pentagon. And this one is a hexagon. So that's a hexagonal prism. So I would like a volunteer to choose one of these four for us to test out Euler's theorem. Choose one of the four. Go ahead. Come on. Okay, Alexandra, pick another one. Pentagonal, very good. So let's try the hexagonal. So Euler's theorem says the number of faces plus the number of vertices is going to equal the number of edges plus 2. So let's find the faces and the edges. So let's count the number of faces. We've got a top and a bottom, that's 2. Since the base is hexagonal, that actually means we're going to have 1, 2, 3, 4, 5, 6 faces going around. So how many faces altogether for a hexagonal prism? Kadir? There's 8. So there's 8 faces. Let's leave out the number of vertices. Let's just leave that as V. But that's going to equal the number of edges plus 2. Let's count the edges. Well, there's 1, 2, 3, 4, 5, 6. So there's 6 edges going around the bottom, which means there's going to be 6 edges going around the top. But then we also have 1, 2, 3, 4, 5, 6. How many edges altogether are there? How many edges altogether, Nathaniel? There are 18 edges. So there's 18 edges plus 2. Now we know how many vertices there are. How many vertices are there? Sharif? Yeah, there's 12 vertices. So we can actually figure out a missing value that we don't know, or we can use it to check and make sure that our structure is correct. And we can count them. The vertices are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12. Any questions on how Euler's theorem works? John?
I know a trick that how to find how many faces there are in a prism. Like say if it's a hexagon, like hexagons usually have 6 sides. You just add 2 to the actual amount of sides of the polygon.
Okay. So you are making a conjecture. You're saying you think, you're theorizing that the number of faces is going to be 2 more than the number of sides of the base, right? Great conjecture. Let's see if it actually proves to be true. So Alexandra chose the pentagonal prism. So go ahead, do Euler's theorem for the pentagonal prism. Go ahead. Count the number of faces. Unfortunately, in this case, I didn't give you the shape on your paper. You're going to have to look up here and try and count them. Yes, Kadir.
Do you want us to leave out one of the variables?
Sure. Why not? John, is your conjecture proving true so far?
Yes.
Okay. So if we use your conjecture, then there's going to be 7 faces because that's 2 more than the number of sides on a pentagon. And that proves to be true. Let's see. Let's count the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I wonder if there's a relationship there as well. So now we know how many edges there are without even having to count them. How many edges should there be? There's 15. So we can count them. There's 5 along the bottom, 5 along the top, and then 1, 2, 3, 4, 5. So there's 15. Anyone have any questions about how Euler's theorem works or what's going on here? Anything at all? John?
Wait, no, never mind. I thought I had another discussion.
Okay.
Does it only work?
Okay. Kadir?
I was gonna say, like, aren't just like the edges like the number of like
The number.
basis, but how much the polygon size? Size of the polygon.
The size of the polygon base
Yeah.
times 3 will get you the number of edges.
Yeah.
Test your theory. You have 2 samples. Do they both prove to be true? Okay, let's see if it works on all. Okay? Also, this works on pyramids as well. Pyramids are similar to prisms except that the faces converge at a single point. So, and the naming convention is similar. So you look at the base, and that base becomes the first part of the name. So triangular pyramid, rectangular pyramid, pentagonal pyramid, hexagonal pyramid. Euler's theorem works for pyramids as well. Any questions so far?
How come the rectangular pyramid isn't called a square pyramid?
If all the sides prove to be congruent, then you would call it a square pyramid. We have the right angles, but we haven't shown that all the sides are congruent. If they were, look at the first picture on your little paper that I gave you. See the tick marks? So that's what you're going to see right now. So, example 1. Our goals for this example is to make sure we understand how to identify and name polyhedra. We want to be able to say whether or not something is a polyhedron. So first we've got yes or no, then we're talking about names, and then we're talking about number of faces, number of vertices, number of edges. And what I would like to do for this example is actually look at it globally. I don't want to look at let's do A, and then let's do B, and then let's do C. I want to say yes or no for A, B, and C. Then I want to name A, B, and C, and then I want to do the Euler's theorem for A, B, and C. So we're kind of comparing them. This is an opportunity to compare 3 different shapes. You have all 3 of them on yours. Mine are stacked a little bit differently. So let's do yes or no for whether or not it's a polyhedron. A, give me a thumbs up if you believe that that's a polyhedron. Good, of course, it is. It is made up of polygons. So this would be, yes, a polyhedron. What about part B? Give me a thumbs up if that is a polyhedron. Yes, it is. What about part C, which I know it's cut off a little bit here, but you have the picture on your paper. Give me a thumbs up if that's a polyhedron. Okay, so nobody says it is. Why is it not? Matthew, you didn't put your thumb up. Why is this not a polyhedron?
It's curved side.
It's got a curve. Very good. Very simple. So, we now know what's a polyhedron. So we're going to look for a name for A and B, and we're going to count the faces, the vertices, and the edges for A and B. But part C, we're now done. It's not a polyhedron, so we're just going to stop there. How about a name? What do you think would be a best name for part A? Best name for part A. Let's get some people involved. Naming, not too intimidating. All right, student number 1, what's the best name for part A?
Rectangular prism.
What do you think, student number 4? Yeah, I would agree that rectangular prism is probably the best name. So this is a rectangular prism. What about part B? What would you call that? I got student 14 and student 15. Student number 14, what would you call it? Okay, student number 15, what would you call it? A hexagonal. It's a hard word to say. Hexagonal is fine, but it's really pronounced hexagonal. Well, I guess it doesn't really matter. But it's a hexagonal pyramid. Any questions about naming? All right, so let's talk about Euler. We want the number of faces, the number of vertices, and the number of edges. So let's do the number of faces, the number of vertices, the number of edges. We can do this by counting, or we can do it partially by counting and part by Euler's theorem. It's totally fine either way. So, you got a paper in front of you, count the number of faces, count the number of vertices, and count the number of edges. And again, you can mark things right on that little paper I gave you. So how many faces are there for a rectangular prism? How many faces are there? Extol, how many faces did you get? 6 faces. Let's see. 1, 2, 3, 4, 5, 6. There are 6 faces. How many vertices? How many vertices? Sebastian, how many vertices did you count? 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 vertices. What about edges? How many edges? Eric? 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, there are 12. Does Euler's theorem hold true?
Yes.
Yeah, add these two together, you get 14, and add 2 to this, you get 14. Absolutely. John, did your conjecture hold true here?
Yeah.
Okay. What about part B? Number of faces. How many faces are there? Nathaniel? There's 7. 1, 2, 3, 4, 5, 6, and then the base is 7. How many vertices are there? Go ahead, John.
7.
There are 7. 1, 2, 3, 4, 5, 6, and then 7. How many edges are there? How many edges? Could you hear? 12. You got 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. There are 12. And if you add these together, you get 14, and add 2 to this, you get 14. And so Euler's theorem holds true. Any questions, comments about counting, Euler's theorem, these objects, these names, anything at all? John, go ahead first.
I have several conjectures about pyramids.
Go ahead.
I noticed that the number of vertices is the same as the number of faces, and the edges are 2 times the amount of the size of the hexagon.
Okay. So I don't know if I gave you enough pictures to experiment with. Maybe I did. So you can look and see if you can prove your conjecture to be true. It's a great idea. I love the thought. Any other comments and questions? All right, so let's see how you do with these two, which are also on that paper. So you can actually just mark it right on your paper. You don't have to write it on your notebook paper if you don't want to. Tell whether it's a polyhedron, and then give it a name, and then find me the number of faces, vertices, and edges. You got 2 questions. You got about 2 minutes. how he did. This time we will go question by question. Part A, what did you put? Student number 20 and then student number 5.
Yes,
Okay, student number 5, what did you say?
Yes, the polyhedron is a square pyramid and has 5 faces, 5 vertices, and 8 edges.
So, yes, it's a square pyramid, 5 faces, 5 vertices, and 8 edges. Sorry about that. What about part B? I got student 14 and student 18. What do you say, student 14?
It's not a polyhedron.
So you just stop there, student 18? Not here. So, Dianara, you were right. It is not a polyhedron. Very good. Any comments or concerns? Yes.
I don't know if anyone said this yet, but a conjecture for pyramids
Mm-hmm.
and the faces and the vertices for a pyramid would be the base polygon, the number of sides of the base polygon plus 1.
Okay.
And for the edges, it would be the number of sides of the base polygon times 2.
Okay. And do you have enough examples to
Yes.
prove it with?
Yes.
And it seems to work?
Yes.
Great. So John definitely said something about that the faces and the vertices were equal to each other, but you're taking it a step further and saying the number will be the number of sides of the base plus 1, and they'll be equal to each other. That's great. Great job. All right. So I had an intention with this example, but I'm pretty much going to scrap it. The intention was really to bring real objects into it rather than these objects that exist only in a classroom. And so homes are based on three-dimensional solids, and so it's a very good concrete example of this. But the question itself is kind of mundane and simplistic. The number of edges of the house, I mean, we could just simply count. So it's not much of a challenge. So I'm just going to forego this question. And I also realized that the checkpoint was a bit too simplistic as well. So I'm going to forego this, but I'm going to use it to just introduce another idea, which is there is a, I believe there are 5 of them, and I'm still learning, so you guys have to bear with me as I learn some of these things as well. There are 5 polyhedron that are regular. There are only 5 of them. And I haven't quite understood yet why there are only 5 of them. It has to do with the angle measurement of the polygons. But this is one of them. This is called an octahedron. So it doesn't have the same type of name that the other ones that we've seen so far have. It is made up of regular triangles. It kind of looks like a pyramid stacked on top of a pyramid going the other way. But one thing that came about with the other class is that when we counted the faces, some people got a little confused with this space inside here. That is not a face. The faces are only what you can see from the outside of the shape. It definitely would have been better had I had shapes sitting around the room on your desks or around the room for you to explore. Unfortunately, I loaned them to somebody several months ago and I never got them back, and that was my mistake. So all we have are the two-dimensional representations of them. So you have to use your creativity and your imagination to realize that this is supposed to be a three-dimensional object that we can turn around and look at from different perspectives. Does anyone have any questions about that? In your textbook, it talks about these 5 regular polyhedron, one of them which is the octahedron. So we'll talk about it at some time in the future. So let's move to the other goal, which is to work with cross-sections. A cross-section arises when you take a plane and slice a solid with it. And the interesting thing is, depending on how you slice the solid, a different shape will arise. Now, on your paper, you have black and white. Up here, I have color. So you're going to have to figure out how to get the color image into your world, because I've pretty much done a lot of the work for you by coloring these things. So, for example, in part A, the question is, what shape is formed by the intersection of the plane and the cube? Key word there, it's a cube. Also, this plane is parallel to the base. So what shape is colored purple? What shape is it? Let me ask a different question. Give me a thumbs up if you know what shape it is. Okay? Good. Ziomara, what shape is it? It's a square. Not a rectangle, it's a square. Well, a square is a rectangle, but more specifically, it's a square because it's a cube. So we're slicing through it parallel to the base. This must be a square. So it's a square. Part B, what happens if we take the plane and slice the cube corner to corner? What shape it represents the intersection? So give me a thumbs up if you can recognize the shape from the image. Good. Kalasia, what shape is it? It's a rectangle. Very good. So that's what we talk about when we talk about cross sections. But here's where it becomes interesting. What if we slice through the cube, but now it's at a different angle? So you're going to have to turn your paper over. Keeping in mind that it's a cube, what shape is emerging now? Eric?
Looks like a trapezoid.
Okay, John? It's a trapezoid. Can you be more specific? Go ahead. Yeah, assuming that the paper is held in a particular way, that we might be able to say that it's an isosceles trapezoid, meaning that this side was congruent to that one. But at the very least, we could say it's a trapezoid. I think it's an isosceles trapezoid, but we'd probably need a little more information. Anyone have any questions on how to interpret what shape the cross-section is when you intersect a shape with a plane? Any questions or concerns? Okay. So, checkpoint, now I can take it a step further. You do not have to copy the text of the question. You got 3 questions, and the diagram you have is on your paper. I made it a little bit bigger, and I left space around it on the back so that you could do things right on the paper. So we've got about 7 minutes for this checkpoint. This is an independent checkpoint. And by the way, B and C are 2 separate questions. C is not based on B. They're 2 separate questions.
I mean, we're gonna have that over.
All right, we are back together as a whole group. So we'll start question by question. Part A. What type of triangle is the cross section? I got student 13 and 17. Student 17. It is an equilateral triangle. Nicely done. Part B. If the edge length of the cube is 1, what's the length of D? I've got student number 1 and student number 5.
Oh, right.
Student number 5. It would be radical 2. If we change the scenario and said that the edge of the cube is 4 radical 2, what's the perimeter of the cross section? I got student 3 and student 8. Student number 8. Comes out to 24. Comments and questions? Sharik and then Kadir.
You know, it says but A is an equilateral. Would regular work too?
Well, I guess equilateral is a regular triangle, but we have a special name for it. It's equilateral. So in the future, just try to make sure regular triangle means equilateral. Yes. Same question? Okay, I can deal with it. All right, any other comments, questions? Good. Draw a line across your paper. Your homework is on page 746. You are doing numbers 11 through 27, 34 to 38, and number 40. Number 40 has several parts, and then one of the other questions has 2 parts, so each part counts separately for a total of 26 points. Please do the at-home tutor or read the next section. Don't forget your EOC is in a couple of